up until now I've been looking at the properties of gases and how they behave. We're now going to start to look at exactly why it is that they behave in those ways, and we're going to do that by looking at the kinetic theory of gases. Now, the kinetic theory of gases, basically it allows those macroscopic properties, so things like the pressure of a gas, so it allows those macroscopic properties to be understood from the perspective of the microscopic nature. So microscopic properties of a gas, so they can be understood by considering the microscopic nature. And in particular the particles themselves that make up the gas. So there are a few assumptions that we're going to make here. When we're talking about gases here, we're really talking about ideal gases again. So there are 5 key assumptions, and they can sort of be, the textbook actually lists about 9, I think, but they're basically these 5 key assumptions that they've sort of split into a couple of extra points or sort of extra elaborations. So we're just going to focus on the 5, and some of these I'll add some detail, and you'll see how it ties in with the textbook if you do cross-reference. The first thing is that a gas contains a large number of identical molecules. When we're talking a large number, one of the extra points that the textbook makes, the large number that we're considering is effectively that it's so large that statistically some of the other things that we'll talk about in these 5 dot points can be treated as like a statistical model. So it consists of a large number of identical molecules in constant random motion. That idea of random motion, just want to talk about that really quickly. That basically means, so this idea of random motion basically means that there is an equal chance of a particle moving in one direction as in the other direction, or another way to think of it, there's no sort of overall movement that you could identify that particles moving in. So it's evenly distributed across all directions, and as a result there's no average direction in which the particles are moving. It's completely random motion. So the second dot point then is about the size of the molecules compared to the volume of the gas itself. So a couple of different ways to state this. So the molecules are very small and very far apart. So that's sort of the easiest way to make sense of this particular assumption. A couple of other ways that you might want to consider it, or another way of wording it, basically saying the same thing just from a different perspective. The volume of each molecule is negligible when compared to the volume of the gas. So the space that the gas in its entirety takes up is quite large in compared to the volume of an individual molecule. Another way of thinking about that is that to say that the volume of the gas is, or most of the volume of the gas is actually empty space. The third one then, so we've got the size or the volume that the molecules can take up. Molecules can undergo collisions, so even though they're very far apart, they do occasionally undergo collisions. So molecules can undergo collisions, and those collisions can occur with each other and with the container walls. So despite the fact that their volume is negligible, they still can undergo collisions, and that's both with the other gas molecules and with the walls of the container. And the collisions with the walls, with the container walls, basically give us that idea of pressure. So collisions with the container walls account for the pressure of the gas. So we can measure the force that's being applied to the containers, the container wall, and so we can then pressure over area. We can figure out, force over area. We can figure out what the pressure is. So the reason why we have that pressure is because of the collisions with the gas molecules against the walls of the container. Now, the next important thing is actually more detail about those collisions. So when those collisions do occur, they do so perfectly elastically. What we mean by that is that there is no loss of kinetic energy. So an elastic collision is one where no kinetic energy is lost. So we can identify then that the total kinetic energy of the particles remains constant. So even though they're bouncing off each other, the total kinetic energy of all of the particles, or all of the molecules, remains the same. And the only reason then we would see a change in that kinetic energy comes back to laws of thermodynamics. So if work is done on the gas, or if thermal energy is added to the gas or removed from it, then the total kinetic energy would change. But while the gas is just existing as it is without any external influence, the total kinetic energy would remain constant. And finally, the last one, there's no attraction or repulsion between the molecules, so there are no intermolecular forces. And that basically then means that the only forces that are occurring on the molecules are during the collisions. So forces are only exerted during those collisions. And otherwise, that then means that molecules are going to move in straight lines. So there's the assumptions about the kinetic theory of gases. You do need to be able to identify them, explain them, understand them. You don't necessarily need to do anything more with that in terms of deriving anything from there. In the textbook they do have a derivation about those particular laws and relating that to some of the properties like pressure, for example. I'm not going to go through that. It's a little bit more involved than what you need to do for these videos. It's more just that you need to have the understanding of those assumptions, but from those assumptions the pressure of a gas can be explained. So the pressure of a gas can be derived. And like I say, if you want to have a look at that derivation, have a look in the textbook. I've used a slightly different, they've used C, I think it is, as a speed, but I'm going to use a different variable just to make it a little bit clearer. So the equation that you can derive from those then is that the pressure is equal to 1/3 Nm on V multiplied by U, or the average, the mean square of the speed, mean square speed of the particles or the molecules. Notice I'm not highlighting that one. This equation's not actually in the data booklet. The reason why I'm mentioning it though is because it follows from the kinetic theory and will link to the next idea we're looking at. I'll just go through and notate what each of these quantities are. So the quantities themselves, P is pressure in pascals, N is the number of molecules in the gas, M is the mass of an individual particle, and that will be measured in kilograms. V is the volume, and as we've seen before, volume is measured in cubic meters. And the last one there, U, I'm not using V here for speed or velocity, using U just to make a bit of a distinction between capital V and lowercase v. Those two can sometimes look a bit similar. So U is the average speed of the particles. So average speed of all the particles, or all molecules in the gas, and that's measured in meters per second. So like I said, we'll have a look at this equation in a little bit more detail in the next video, but ultimately when we're looking at pressure, if we know the number of molecules, the volume, the mass of the gas, and the average kinetic energy, average speed of the particles, we can then calculate the pressure.